तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last class we were discussing about softening. We have also seen what are the different methods that can be employed to remove hardness. Those are chemical precipitation and ion exchange. Chemical precipitation, we usually use lime and soda ash, and we can either treat the entire water or we can treat partially and blend it. Okay, so that is known as split treatment, and we have seen that when we go for ion exchange process, especially if you want to remove the hardness completely, we have to go for ion exchange process. Today we will be discussing about another treatment process which is commonly used in all water treatment plants, that is filtration. What is the need of filtration? Filtration is a polishing unit, because we have seen that sedimentation process and coagulation flocculation process or softening process, these processes will not remove the solids whatever is present in the water completely, because after coagulation and flocculation we are going for the settling. The settling will not be 100% efficient. So what will happen? Some flocks will be remaining in the liquid. Similarly, the softening also, the precipitation will not be completed fast, or the settling will not be 100% efficient. So some flocks will be remaining in the water. So if you want to remove all these flocks, whatever is left over after coagulation, flocculation or softening process, we have to go for filtration. So filtration is basically a polishing treatment unit. But if the quality of water is good and the turbidity is low, then we can use it as a salt treatment unit followed by chlorination. So that's what I have written here. Filtration is a polishing step to remove small flocks or precipitant particles not removed in the settling of coagulated or softened waters. So because if the flocks are remaining there, it will not be aesthetically appealing. So the major objective of filtration is to improve the aesthetic of the water. Beyond that one, if turbidity is present, okay, after the filtration we are going for chlorination or disinfection. If turbidity is present in the water, disinfection will not be effective. The reason is the pathogens or the microorganism whatever is present in the water, that will be taking shelter under these turbid particles. So the chlorination will not be effective and the treated water may cause many problems. That means it will not be bacteriologically safe. So in that point of view also we have to go for filtration to remove turbidity. So the drinking water standard according to Bureau of Indian Standards is the turbidity should not be more than 1 NTU. So if you want to achieve that one, it will not be possible by simple plain sedimentation or coagulation and flocculation. So filtration is an essential unit. So as I mentioned already, sometimes we can go for direct filtration, which is a primary turbidity removal unit. After this direct filtration, we can go for chlorination. This direct filtration is employed only if the turbidity of the water is less than 20 NTU. And filtration can also remove pathogens, but not a complete treatment unit for bacteriological safety. It can remove around 99% of the pathogens, but again that 1% is left over, so that can cause diseases. So it cannot be considered as a complete treatment for pathogen removal. Now we will come to the different types of filters. Types of filters can be classified based upon the direction of flow of water, whether it is downflow mode or upflow mode the filter is operating, or it based upon the filter media, because either it is sand, we can go for gravel, we can go for dual media, we can go for mixed media filters, or sometimes we can go for activated carbon filters or diatomaceous earth filters. So depending upon the filter media also we can classify the filters into different categories. And another classification is based upon the driving force. What is the driving force which is responsible for the filtration? So it can be gravity, because the water will be staying over the filter bed at a constant head, and because of the gravity it will be filtering through the filter. So that is one type of a filter. And another one is we are applying the water under high pressure. So the pressure will be the driving force for the filtration. And another classification is method of flow control. So how are you going to control the flow in the filter? And the last one is filtration rate, because certain filters are designed for having a constant rate and some filters operate at a declining rate or variable rate filtration. So these are the major classification of filtration. Once again I will tell, depending upon the direction of flow of water, types of filter media, driving force whatever we are applying, how we are controlling the rate of filtration, and the last one is how the rate of flow varies. And coming to the practice, most common filter being used in most of the water treatment plants are granular medium and diatomaceous earth. This is also commonly used in swimming pools and industrial applications. And another type of a filter is pre-cut filters. Okay, it consists of a porous septa, and we add turbid particle or clay particle, and that will be acting as the filter. Okay, so already I have discussed how we can classify the filters. Okay, this gives another type of classification. We can classify the filters again into surface filters and depth filters. Surface filters are the one where depth is not important. That means the name itself emphasizes the filtration is taking place in the surface. So the mechanism of filtration is nothing but simple straining. So material is removed in the surface. The examples of surface filters are screens, strainers, micro strainers, cloth filters and vacuum filters. And depth filters, here entire depth of the filter is being used for the cleaning of water. So depth is very, very important here. And an example of this depth filter is gravity filter, and another examples are groundwater recharging and flow through porous media. All these things are coming under depth filters. Now we will discuss about the most commonly used filters in water treatment plants. Those are slow sand filters and rapid sand filters. Slow sand filter is the simplest filter without any mechanical equipment. So this can be used in places where the water is relatively clean. That means the turbidity is less than 20 NDU, and this slow sand filters can take pre-treated water or raw water as such. And this can be used where the land, labor and sand is available without much problem and they are not very costly. In such cases we can go for slow sand filter. So here the pore size is very, very small, and the mechanism of removal is by straining. That means the sand will be acting as a sieve, and whatever particle is coming, it will be screened or strained through the sand. So that is the mechanism of particle removal. And what will happen with respect to time, in the surface of the filter there will be a biological growth. Okay, that is known as dirty layer. So this dirty layer is responsible for removing any dissolved solids, mainly organic matter present in the water. So when the water with turbidity and this dissolved organic matter passes through this slow sand filter, turbidity will be removed by the straining action, and because of this dirty layer or slime layer, whatever is formed on the surface of the filter, okay, which consists of very, very active microorganism. These microorganisms, what they will do, whatever organic matter present in the water, they will be eating away the organic matter, and since the pore size is very, very small, okay, it will be able to remove a great extent the microorganism present in the water also. So, whatever water coming out of the filter will be completely clean, okay. And mostly the removal in slow sand filters take place in the top 2 inches. So, the bottom portion of the slow sand filter will be relatively clean. So, that is why the slow sand filter is known as a surface filter, and usually the sand size used in slow sand filters are very fine compared to rapid sand filter. The sand size varies from 0.25 mm to 0.35 mm, and the uniformity coefficient varies from 3 to 4, and usually a bed depth of 1 meter is provided in the slow sand filter, and as the name itself tells, the flow rate is very slow in slow sand filter. So, if you want to have a large quantity of water to be treated, the area required is very high. So, it is a land intensive process, but for small community and where the water is of reasonably good quality, it is the best treatment option, because with a single unit we can achieve the complete treatment. Then after the filtration we can go for chlorination and we will be getting water of potable quality. So, if you want to see what is the operational conditions of a slow sand filter, usually the filter box or the total height of the filter varies from 2.7 to 3 meters with a freeboard of around 0.2 meter, and usually the sand height will be 2 meters and the sand height will be 1 meter, and there will be a gravel layer under the sand that will be around 0.3 meter, and the under drainage system will be taking another 0.2 meter, and the height of the water column standing above the filter will be around 1 meter. So, we will see once again, total height is around 2.7 to 3 meter. So, freeboard is around 0.2 meter and water column is 1 meter, sand depth is 1 meter and gravel depth is 0.3 meter and under drainage system is around 0.2 meter. So, altogether it comes 2.7. So, that is what I told, the height varies from 2.7 to 3 meter. Why we are providing this 1 meter height of sand? Because we have seen that the mechanism of particle removal in slow sand filter is merely straining and microbial action, and most of the cleaning is taking place in the top 2-inch portion. So, what will happen with respect to time? The top portion of the sand will be getting clogged because of the turbid particle and the microbial growth. So, at that time the rate of filtration will be coming down drastically. So, how can we clean the filter? Okay, since it is a surface filter, we have to clean only the surface. That means we have to remove the dirty layer from the top. That means around 10 centimeter depth of the filter sand we have to remove. So, what will happen? You have already 1 meter depth of sand. So, you are removing around 10 meter depth of the sand from the top. So, remaining 90 centimeter will be there. So, the filter will be running perfectly alright. Okay. And at any case, the filter sand depth should not go beyond 0.4 to 0.5 meter. So, if you fill the filter, it can be operated without sand replacement for 2 to 3 years, because every time we are removing only 10 centimeter and yearly we may have to remove twice or once or twice depending upon the quality of raw water coming to the filter. So, it is very easy, because once the height reaches 0.4 meter, we have to remove entire sand and replace it with new sand, and we will be getting the water, clean water through the under drainage system. Then we can collect it in the tank and provide a weir and measure the quantity of water coming if you are interested. And the flow rate of slow sand filter is very low. It is only 130 to 150 liter per meter square per hour, or if you want to have in linear meters, it varies from 0.1 to 0.2 meter per hour. So, it is very low. So, whenever we talk about different treatment units, most of the time what we do, we provide a standby unit, because whenever the cleaning is required, so other units have to be there in operational condition. But in case of slow sand filters, it is not in that way, because if you have 2 filters So both the filters can run continuously with a flow rate of 0.1 meter per hour. So that is the recommended value. But during the cleaning, one filter you can close and the other filter can be overloaded up to 0.2 meter per hour. So what will happen? We don't have to go for another filter which is just a standby one. So the one already existing can take overloading, but we have to have proper inlet arrangement so that the sand surface of the slow sand filter will not be getting affected, because your dirty layer or the microbial slime layer will be there over the sand bed. So if it get disturbed, okay, the quality of filtrate will be affecting. So this I have already discussed. The cleaning is by scraping the top layer, and rate of filtration is very low. That is why the name slow sand filter has come. And one more thing, when we go for slow sand filter, the sand whatever we are getting as the builder's sand or something like that, we can directly use that sand. No need of grading or preparing that sand for slow sand filter. Okay, the sand as such we can dump it to the filter. Otherwise, if you want to grade it, the cost of that sand filter will be very high. So even if you use the sand as it is available, it is not going to hamper the efficiency of the system much. Now we will see rapid sand filters. So of course, here the flow rate is very high compared to the slow sand filter. So it is the filtration is by gravity, so it is known as rapid gravity filtration, and this is the one most commonly used in water treatment plant. And here the media is coarser compared to slow sand filter. See, we can see the effective size varies from 0.4 to 0.75 mm, 0.6 mm, this is the usual range, but it can go up to 0.75 mm, and uniformity coefficient is 1.3 to 1.7, and the filtration is very high. We can see the rate of filtration is 4000 to 6000 liters per meter squared per hour. Or if you want to have the velocity in linear, in velocity terms, the flow rate is in the range of 4.8 to 6 meter per hour, and even we can go up to 10 meter per hour. And the most important difference between rapid sand filter and slow sand filter is the removal is with depth. Okay, it is not only the straining which is responsible for the removal of colloidal particle in rapid sand filters. Okay, and since the entire filter media is used for the removal of particulate or turbidity, so the cleaning cannot be done by scraping the top layer. We have to clean the entire filter media. So usually we adopt backwashing for the cleaning of rapid sand filter, and most commonly used filter media is sand, and sometimes people use coal, anthracite, coconut shell and ballastic stone, etc. Anyway, we will come back to this rapid sand filter in detail afterwards. Before that, we will see what is this dual media or multimedia filter, because as we have discussed, the rapid sand filter most of the time we use sand as the filter media. But what happens if you use sand, okay, and we are going for backwashing? What will happen? In backwashing, everything will be lifted up, or the entire filter will be in an expanded stage or in a fluidized stage. And once we remove the backwash or we reduce the backwash velocity, the particles will be settling down. So of course, the coarse particulate matter will be coming in the bottom, and the medium one in the middle, and the finest one in the top. So if you see the pore size distribution throughout the depth of the filter, how it will be? The pore size will be least in the topmost portion, and it will be gradually increasing, and pore size will be maximum in the bottom. But if you look into the mechanism of filtration, this is not the advisable pore size distribution. If you can have the maximum pore size at the top and the minimum in the bottom, the filter can be used much more effectively. So that is the purpose of this dual media filter. So here what we are doing is, we are making the combination of two media with different density. So what will happen? The coarser media with lighter, means the coarser media with low density. In the backwash, what will happen? It will be staying in the top, and the finer media with high density will be in the bottom of the filter. So, we will be getting a pore size distribution somewhat the other way. That means high pore size will be there in the top and lower pore size will be in the bottom. So, this will increase the efficiency of the filtration. So, if you go for dual sand filter, we can increase the filtration rate considerably compared to sand filter, rapid sand filter. Okay. Anyway, we will come back to this one, the pore size distribution, after discussing in detail about rapid sand filtration. And another one is activated carbon filters and pressure filters. Activated carbon filters or pressure filters usually used in industries. Okay. So, they will be removing turbidity as well as the dissolved solids present in the water, because activated carbon, we all know it is a very good adsorbent. So, filtration as well as adsorption will be taking place simultaneously. So, depending upon the quality of raw water, we can decide which type of filter we have to use. Okay. So, and it can remove even dissolved gases. So, most of the time these filters are operated in closed system and more head loss is permitted, because the filter is running under high pressure. So, it can take more head loss, and usually it is used for groundwater purification where Fe and Mn has to be removed, and this is used only in small installations like swimming pools or some industrial complexes, etc. But in usual practice, wherever community water treatment plants are there, we usually won't go for pressure filters, because these pressure filters are having various disadvantages. The reason is it is operating under high pressure. So, what will happen? The control of flow is very difficult, and another thing is, since the contact time is very less, the filtration is taking place under high pressure. So, if you use it as a chlorination unit also, the chlorine will not be getting enough contact time. So, the disinfection will not be proper. Another thing is, it is in a closed cylindrical shape. So, examination of the interior of the filter is very difficult. So, we won't be able to make out how effective the filtration is taking place, and this is more serious in case of backwashing. We won't be able to make sure whether the filter bed is expanding according to the requirement, because unless the filter bed is expanded properly, what will happen? The turbid particles, whatever is attached to the filter media, will not be coming out. So, we have to have a certain percentage of expansion, but since it is invisible inside the pressure filter, so most of the time it will be very difficult to find out what is the effectiveness of backwashing. And because of its geometry, what will happen? The backwater gutters, whatever the dirty water coming after backwashing, it is not distributed properly on the surface of the filter. So, what happens? Okay, the collection of water after backwashing is also very difficult. Okay, and another disadvantage is it is working under high pressure. So, you see the outlet is under high pressure, and if you suddenly release the pressure in the inlet, what will happen? Entire filter bed will be getting disturbed, and you will be getting a very bad quality of effluent in the outlet. So, these are the disadvantages of pressure filter. So, because of these disadvantages, pressure filter is used only very limited places, especially in swimming pools and industrial operations. And one advantage of this pressure filter is it can have a very high filtration rate, because the filtration is taking place under pressure. The filtration rate is very high. So, wherever the space is a constraint, so we can go for the pressure filtration. And the last one is cake or pre-coat filtration. So, usually diatomaceous earth filters are used, and they are mobile units for water purification. Now, whenever we have to have a water treatment unit and which is mobile, okay, so at that time we can go for this pre-coat filters. Okay, it is very easy to move from one place to another place. Now, we will come back to the rapid sand filter, which is the most commonly used filter in water treatment plant. And we have seen that Slosan filter, the removal of suspended particles or the turbid particle is taking place because of the staining. So, only the top layer of the Slosan filter is being used. But in rapid sand filter, it is a depth filtration. So, entire depth of the filter is being used for the cleaning purpose. So, if staining is not the only mechanism, then what are the different mechanisms those are involved in the cleaning process when we use a rapid sand filter. So, the mechanisms can be classified into two categories. One is the transport step, another one is the attachment step. So, the removal is taking place because of the combination of these two processes, the transport and the attachment. Transport means from the bulk liquid the particle is moving towards the filter media, okay. And in attachment step, what is happening? Once the particle comes in the vicinity of the filter media, it is getting attached to the filter media and getting removed. That is known as the attachment step, okay. So, we will see what are the physical parameters that affect the transport mechanism. Those are the viscosity of water, filtration rate, size of the media, size and density of the particle, okay. Here we can see, okay, it is independent of the chemical properties of the particles present or the turbidity present, okay. So, either it is the flux by coagulation, flocculation, or the flux formed after softening, or it is just turbidity after adding coagulants or without coagulants, okay. It is independent. So, the efficiency will be depending upon the viscosity of the water, or in other words the temperature of the water, and filtration rate. If you have high filtration rate, naturally the efficiency will be less, and size of the media and size and density of the particle, okay. Now, we will see what are the different transport mechanism, okay. First one is mechanical straining, okay. Here also mechanical straining will be taking place. So, for example, we are having the filter media. So, if 3 filter media is there and if they are sitting closely to each other, what will happen? There will be a pore in between that one. So, if the turbid particle size is smaller, bigger than that pore, what will happen? That can be get removed by straining action. And with respect to time, what will happen? This pore size in between these particles, I will just draw it in the blackboard. So, these are the filter media. The particles are here. So, here you can see there is a space, okay. The particle can go through this space, okay. But if your turbid particle is larger than this pore size, whatever is there in between this filter media, what will happen? It will be getting removed. And with respect to time, what will happen? More and more particle will be coming and sitting here. So, the pore size will be getting decrease and decrease with respect to time. So, more and more finer particles will be removed by the staining action. So, this is the mechanical staining, okay. Whenever the particles are there, in between the pores will be there. So, depending upon the pore size, the particle can be removed. So, if you want to find out the efficiency because of this mechanical staining, we can use this formula 7 by 3 into dP by dm all raised to 3 by 2 into 1 by 1 minus epsilon, where dP is the diameter of the turbid particles and dm is the diameter of the filter media and epsilon is the porosity of the filter media. And next one is gravitational settling. Here what is happening is, so there are many filter media or filter that grains are there. So, in between this filter media, so there will be small pockets. So, each of these pockets will be acting as a sedimentation tank. So, what will happen? There the particle whatever is coming from the bulk liquid will be moving, and in that pocket it will be settling because of the gravitational effect. So, that is the second mechanism of transport, that means gravitational settling. So, the particle, each pockets of whatever the space available between the filter media, that is acting as a settling basin. So, the efficiency by gravitational settling can be find out using this formula, settling velocity divided by superficial velocity of particle. And third one is interception. So, you know, whenever there is a filter media, so there are n number of filter media in a filter, and the particles are, because the filter media is stationary there and the bulk liquid is moving from the top or from the bottom. So, what will happen? Okay, the water, when it comes and passes through the filter media, so it will be going away like this because of this boundary layer effect. So, what will happen if the streamline is something like this and a particle is here? So, the distance between the filter media and this streamline is less than the diameter of this particle. Then what will happen? This particle will be hitting on the filter media. So, once it is touch the filter media, we are assuming that it is getting removed. So, same thing is happening here also. So, filter media and these are the streamlines, and the distance between the filter media and the streamline is less than the diameter of the particle to be removed. So, that is known as interception. So, lot of particle can be removed by this mechanism. So, this is the third transport step. And the fourth one is inertial impaction, because we know that the turbid particles are having high density compared to the water, and here the filter media is there and water is flowing, and because of the filter media the water is deviating in its flow path. So, what will happen? Since it is having high mass, okay, high density, so it will be having an inertia. So, it may not be following the streamline of water. So, it will be taking another path like this. See, because of the inertia, it may be taking a straight path. So, because of that one, what will happen? This particle can come and hit on the filter media. Okay, here also it is same thing is happening. The water is moving in this direction. Okay, here also the water is moving in this direction. Because of the inertia of the particle, it is not deviating its direction of motion. It is moving in a straight line and coming and hitting the filter media. Once it is touch the filter media, because of the attachment step process, it is getting removed from the system. So, another one is Brownian motion. So, Brownian motion, you know that sometimes colloidal particles are so small. Okay, so their surface area means surface phenomena is much predominant compared to their mass. So, what will happen? The Brownian motion or random movement of these particles will be taking place. Okay, this is the case for very small particles, colloidal particles. So, what will happen? The streamline is like this, or the water is moving like this. So, the particle is there which is following the streamline because of the random motion or the Brownian movement. So, this will be moving in zigzag direction, and in that sometimes it may come and hit the filter media. So, once it hit the filter media, it will be getting removed from the system. Okay, here also we can see that this particle, it was actually in this streamline. So, because of the random motion or the Brownian diffusion, it is coming and it is hitting this filter media, and as a result it is getting removed. And this one is another example. This is direct interception. So, some streamlines are directly coming and hitting the filter media. See, the water is flowing in this direction and that is having some turbid particle. So, if it is not deviating or it is big enough so that the random motion is not so predominant, so what will happen? It is following the same path and comes and hit the filter media. So, it can also get removed. So, these are the different transport phenomena. So, once again we will see the different transport phenomena. One is the mechanical straining. So, how it is happening we have seen, because in between the filter media, okay, there will be pores. So, if the pore size is lower than the particle diameter, so naturally it will be getting removed, and with respect to time the pore size will be getting smaller and smaller. So, more and more finer particles will be getting removed. Second one is gravitational settling. Here what is happening? The space in between the filter media is acting as a settling tank. So, the particles will be settling. So, that is another transport step. The third one is inertial impaction, because the particles are denser than water. So, it will be having inertia to follow the same path which it was moving, and the water will be taking a different path because of the filter media. So, because of that inertia it will be coming and hitting. And another one is direct interception. That means if the streamline or the direction of path is directly coming and hitting the filter media. And the last one is because of Brownian motion. So, what will happen? Because of the random motion, the particle can come and hit the filter media. So, there is another transport phenomena, that is orthokinetic flocculation. Okay. When we were discussing about coagulation and flocculation, we have seen that there are many mechanical and non-mechanical flocculators, especially orthoflocculation is concerned. So, the filter media itself is acting as a flocculator. So, with respect to time, what will happen? If it is a destabilized particle and if it moves through the filter bed, what will happen? There will be a velocity gradient. So, the particles, there is a chance that many particles will be coming in contact with each other because of the relative velocity, and bigger flocks can form, and that can also help the removal. So, till now we were discussing how the particle is coming in contact with the filter media. Okay. So, that is the transport step. From the bulk it is coming and sitting on the filter media. So, if it just comes and touches there, okay, it is not being removed from the system. Okay. So, if there is no force which can hold the turbid particles to the filter media, then what will happen? It will be again detaching from the filter media and going through the coming out through the bulk liquid. So, there should be some attachment step. So, we will see what all are the attachment step mechanisms. So, those are electrical double layer interaction, then the second one is van der Waals forces, and the third one is mutual adsorption or bridging. So, we are very familiar about these mechanisms. We have seen in detail these mechanisms when we were discussing about coagulation and flocculation. So, in coagulation, how the particles are destabilized and bringing together, the mechanisms were this one: ionic layer compression, adsorption and charge neutralization. Then this van der Waals forces are also coming into picture, that ionic layer compression, then mutual adsorption or bridging. So, in other way we can tell that in coagulation and flocculation, in the mechanism are the same. One is a static unit and other one is a dynamic system. So, that is the only difference. So, what is happening? Okay, if you consider this electrical double layer interaction, how it is taking place in the filter. So, there filter media is there and your particulate matter is coming. So, where the double layer is formed, okay, the filter media most of the time we are using sand. So, naturally that also will be having some ions attached to that one, and the liquid is moving through that filter media. So, what will happen? The ionic layer will be just shearing off, or the electrical double layer is just shearing off. So, what will happen? There may be streaming potential developed across the filter. Because of this one streaming potential, what will happen? The filter particles will be having a potential difference in the top and the bottom. That means the filter media in the top may be having high negative charge compared to the bottom one. The bottom one will be having high positive charge compared to the top one. Similarly, the particulate matter whatever is present in the system will be having the charge in the other way. So, because of that one there are chances of particles getting attached. And another one is because many turbid particles are moving along with the bulk liquid. So, there are chances of these colloidal particles themselves interacting with each other. So, as we have seen in coagulation, when the colloidal particles come close to each other, okay, when the van der Waals force is more predominant than the repulsive force because of the ionic layer. So, what will happen? The particles will be getting attached. So, that is what is happening in van der Waals forces. Then sometimes what will happen? Because of the functional groups present in the filter media, there will be mutual adsorption and bridging. So, we have seen that the filtration mechanism basically can be classified into two groups, transport mechanism and attachment mechanism, and attachment mechanism is almost similar to that of coagulation. So, in filtration also, if we add coagulants and destabilize the particle, the removal will be much easier compared to the colloidal particle which is not destabilized. This is true when we talk about rapid sand filter, okay, which is a depth filter. The mechanism is entirely different from that of slow sand filter. But when we talk about slow sand filter, the removal can happen whether the particle is destabilized or it is as such. So, in rapid sand filter, it is always advisable to go for coagulation or add little coagulant dose before going for the filtration, because the turbid particles will be getting destabilized and the removal will be much easier. Okay. This is important when we go for direct filtration, because this filtration, though we told that it is a polishing unit, sometimes it can use as a only treatment system, okay, when the turbidity is very low and the water quality is relatively good. So, if the turbidity is less than 20 NTU, so what we can do is add little coagulant dose to the water to be treated, then allow it to pass through the rapid sand filter. So, by adding the coagulant dose, what is happening? The particles are getting destabilized because of the chemical reactions whatever we have seen earlier, and once the destabilized particle comes through the filter, it will be getting removed because of all these mechanisms. So, it is always better to add coagulant dose when we go for direct filtration to improve the efficiency, because the mechanisms are like this. Now, we will see, okay, how can we find out the efficiency of the filter, or if you know that this is the turbidity, okay, of the inlet water, and when we are using a particular length of filter, we are getting the effluent quality of something. So, if you want to improve the efficiency, how much is the filter depth we need, or what is the performance of the filter, whether we can predict the performance of the filter properly. See, this is the filter and we can have different manometers to measure the head loss at different points. The water is coming like this. Most of the time, especially in the community water treatment plants, we use downward filtration. So, influent is coming and here there will be a constant water head available, and this is the filter media, and filter media depth varies from 0.6 to 0.75 meters, and you will be having a gravel bed and under drainage system to collect the treated water, and whenever it is required to backwash the filter, okay, we can backwash using this under drainage system, and this is the effluent. So, initial turbidity is C0 and this is the turbidity C at any T. So, if you plot the C by C0 versus depth, okay, at different depth, if you plot the C by C0, it is like this. Okay, initially we can see that with respect to depth, the C by C0 is reducing considerably. That means, okay, if you take after 10 centimeter depth of the filter, the turbidity reduction is not so much, but it is increasing gradually, and at the bottom of the filter almost everything is getting removed. But with respect to time, what will happen? The turbidity removal efficiency is getting reduced and reduced. Here we can see the reduction is not much. So, this is different curves at different times. Okay, this is initially, that means the filter is just started operating, and as the time progress, the filter operation efficiency is coming down. Okay, so this is with respect to turbidity, and if you plot the same with respect to head loss, what will happen? Okay, this is the head loss and with respect to depth. Okay, so this is when T equal to 0. Okay, the head loss will be very less. Okay, it is the head loss. Okay, we will be getting that hydrostatic pressure line. Then as the filtration increases, the head loss will be increasing. We can see that here. Okay, we can see the slope itself is changing. So, Iwasaki in 1937 he has developed this equation. So, how the filtration efficiency depending upon the length of filter. So, he has shown that the rate of change of concentration of the tablet particle with respect to length is proportional to the initial concentration of the tablet particle, or we can write like this: dC by dl equal to minus gamma into C, where gamma is a constant. This is known as filter coefficient, or if you integrate this one, we will get ln C by C naught is equal to minus lambda L, okay, and where when L equal to C, L equal to 0, C is equal to C naught, okay, and here lambda is the filter coefficient, or we can write like this: C is equal to C naught into e raised to minus lambda L. So, if you know what is the initial turbidity of the water, and if you know what is the length and the filter coefficient, we can find out what is the turbidity that is coming out after the filtration. So, this filter coefficient we can find out by conducting the laboratory experiments or conducting experiments. Okay, what we have to do is, you know the different lengths, okay, we have to find out the C value, whatever we have seen earlier. With respect to length, we can find out C by C naught with respect to depth. Depth is nothing but the length of the filter media. So, we will be getting the curve like this. From this one, we can find out the value of lambda. Once the value of lambda is found out, we can predict what is the performance of the filter. And again, Iwasaki shown that this lambda is not a constant, because Iwasaki was assuming that this lambda is a constant, but Ive has found out that this lambda is not a constant and it changes with respect to time, okay, or it is a function of time or specific deposit. So, we were discussing about that straining. So, what was happening? The in between the filter matrix, okay, there is pores. So, with respect to time, what will happen? The pore size will be decreasing with respect to the specific deposit. So, the pores will be coming smaller and smaller, okay. So, the filtration efficiency will be increasing to a certain extent. So, if the pore become still smaller, what will happen? The velocity, the pore velocity or the velocity with which the water is flowing through the pore will be increasing drastically, because your Q is a constant. So, what will happen? With high velocity, whatever particle is already attached to the filter media, it will be shearing off and coming along with the liquid. So, what will happen? Okay, to a certain extent, the filtration efficiency was increasing with respect to time or this specific deposit, and after that one, what will happen? The filtration efficiency will be decreasing with respect to the effluent quality. So, that is what is written here. Lambda is a function of sigma, where sigma is the specific deposit. That means, what is the amount of turbid particle deposited per unit mass or unit volume of the filter media, that is a specific deposit, and that is also a function of time. So, we can write lambda is equal to lambda naught, which is equal to a constant into the specific deposit at that time. But again, we have seen, isn't it, the lambda is increasing with respect to time to a certain extent, and after that it will decrease. So, the equation can be modified like this: lambda is equal to lambda naught. Lambda naught is the filter coefficient of the clean filter plus k into sigma minus phi into sigma squared minus epsilon naught minus sigma, because epsilon naught is the porosity and sigma is the specific deposit. So, epsilon naught minus sigma is the effective porosity, because the pore is getting reduced and reduced, and phi is a constant. So, this is very, very important. So, if you want to see that in filter operation, if you plot this lambda, that means filter coefficient and sigma. So, up to a certain value, what will happen? The efficiency of the filter is getting increased. Okay, we can see that efficiency is increased, or C by C naught value is decreasing. So, up to this point, this is known as maturation of filter, and after that what is happening? The quality is deteriorating. So, what is the reason? Because the sigma is the specific deposit. What is the amount of particle deposited? So, if the sigma is increased after a certain limit, what will happen? The pore velocity will be very, very high. So, that pore velocity causes the shearing of the particle whatever is already sitting on the filter media. So what will happen with respect to time, more and more particle is will come out along with the effluent. So the quality will be deteriorating drastically. So we have to stop the filter operation at this stage. This is the same thing represented in terms of C by C naught and time. So we can see that as soon as we start operating a fresh filter, the C by C naught value will be relatively higher. Then with respect to time, it will be decreasing and you will be getting a lowest value here. So this is the one we call it as ripening of the filter. At this time, the filter will be operating at its optimum condition. That means the pore size is in such a way that it will be removing the particles maximum and velocity is also reasonable. But what will happen? Okay, again the filter is being operated, more and more particle will be definitely coming and sitting on the particles. So C by C naught will be increasing. So after a specified limit, okay, that means the standard is 1 NDU. So if this value crosses that one, we have to stop the filter operation and bypass the filter and start it again. So now we will see why the head loss is taking place in the filter. So if you see the head loss development in the gravity filter, we can see this is the static pressure head. Okay, if you have a water column in a container, so how the pressure distribution? So that is this one, a 45-degree line. Okay, and it is static pressure. Now flow is taking place, and this is the clean filter. Okay, the filter is there. So this pressure drop is because of the filter bed itself, because the flow has to, or the water has to pass through the filter media. So the clean filter will be generating some head loss. So that is this one, and afterwards what will happen? As the filtration increases or as the filtration progresses, the head loss will be increasing. We can see that the head loss will be more, okay, the rate of increase is more in the top. So what is happening? Especially the sand filter, rapid sand filter, fine particles will be in the top. So the tablet particles will be coming and sitting in the top, and the pore size will be getting reduced considerably here. So we can see that the head loss will be very high and it is going like this. Okay, so this is the head loss profile when the filter is almost the middle way through. Okay, after the cleaning and to the next cleaning, so this is the middle way. Okay, and if you continue the filtration, what will happen? Sometimes negative head can generate. So if the head loss in the filter is more than the head available here, so this negative head can occur in the filter, and this negative head occurring is very bad in the filter, because the filtration efficiency will be drastically reducing. So we should avoid negative pressure development in the filter. So how to find out the filter head loss and how to calculate that one and how can we clean the filter, those things we will discuss tomorrow's class, and today we will see what all the things we have learned till now. So we have seen that filtration is a polishing operation. Okay, so the coagulation flocculation unit and or the softening unit, after the treatment what will happen? The flocks may not be removed completely from the system. So some flocks will be coming out along with the effluent in the clariflocculator or the softening system. So that is not aesthetically appealing. So we have to remove that tablet particle. Moreover, if the water is having tablet particles, the chlorination will not be effective, because as I have already mentioned, the bacteria will be, or the microorganism will be going and getting attached to the tablet particle, and it will be acting as a protective layer or protection for the microorganism. So it will be escaping from the disinfection process, and based upon the operation or the material or the rate of filtration, we can classify the filters into different categories. But the most important classification is surface filters and depth filters based upon the mechanism of filter. Okay, and Slow sand filter and rapid sand filter are the most commonly used filters in water treatment, and pressure sand filters are being used in swimming pools and the places where the space is a constraint. In slow sand filter, the mechanism of filtration is straining. So, only the top layer is taking part in the removal of suspended or turbid particles and even dissolved organic matter, because in the slow sand filter a dirty layer of active microorganism will be formed that will be taking part in the cleaning of all the other contamination. So, in the top 2 inches will be removing almost all the contaminant, and as the water moves through the remaining depth of around 0.6 to 0.8 meter, what will happen? Everything will be getting removed. And rapid sand filter is a depth filter. The mechanism of particle removal is entirely different from that of slow sand filter. So, the mechanism is can be classified into 2 categories. One is transport mechanism and another one is attachment mechanism. Transport mechanism can be either straining, gravitational settling, inertial impaction, direct interception, Brownian motion, any of these ones, or orthokinetic flocculation. And attachment steps can be double layer interaction, van der Waals forces, and adsorption and interparticle bridging. Or we can tell that the mechanism wise rapid sand filtration and coagulation are almost same. One is a static system and another one is a dynamic system. So, it is always advisable to have coagulant in rapid sand filter.